Good morning, ladies and gentlemen. This is Paolo Valvo from the University of Pisa, Italy. My talk is about the development of a physically consistent virtual crack closure technique, VCCT, to account for possible contact and interpenetration that may occur between the crack faces. According to Irwin's crack closure integral concept, the energy release rate G can be evaluated by computing the work that would be necessary to close the crack. Figure A shows a cracked body with an initial crack of length A. In figure B, we have the extended crack by an amount delta A, and figure C shows the closure of the crack. If no interpenetration occurs between the crack faces, then the forces necessary to close the crack, shown in figure C as the distributed forces Qx and Qz in the x and z directions, respectively, are simply equal to the stresses acting at the crack tip in the initial configuration. So Qx will be equal to the shear stresses tau Zx, while Qz will be equal to the normal stresses sigma z. We can calculate the work done by the crack closure forces, and if we take the limit of the ratio of this work delta W over the new area of crack created, B delta A, for delta A that approaches 0, we have an expression for the energy release rate. And for symmetric cracks, it may be noted that the two addends appearing in the expression of G simply correspond to the mode 1 and mode 2 contributions to the energy release rate. It may happen that depending on the restraints and loading boundary conditions, the elastic solution may predict interpenetration of the crack faces. Figure A again shows a cracked body with an initial crack of length A. Figure B shows the extended crack, and in this case the crack tip point C splits into 2 points, C plus and C minus, which undergo a negative relative displacement delta U Z in the Z direction. In this case, we have an overlapping of the crack faces, which may be prevented by introducing a suitable distribution of contact pressure Px, as shown in figure C. If we want to close the crack starting from this configuration with the contact pressure forces, the crack closure forces Qx and Qz have to account for the contact pressure P, and in particular the normal crack closure force Qz will be equal to the normal stress sigma z plus the contact pressure P. The same concepts can be implemented within a finite element environment. In this case, Irwin's crack closure integral becomes the so-called virtual crack closure technique. Figure A shows a part of the finite element mesh. We consider a plane elasticity problem. We are in the neighborhood of the crack tip C, and the crack has an initial length A. In figure B, we consider an extension of the crack by a length delta A, and the crack tip node C splits into 2 points, C minus and C plus, and we denote with delta UZ and delta UX the relative displacement between these 2 points. To close the crack, in figure C, we apply closure forces Qx and Qz. And again, if no interpenetration occurs, the forces necessary to close the crack are simply equal to the nodal forces acting at the crack tip before crack extension. So Qx is equal to Fx and Qz is equal to Fz. We can calculate the crack closure work, delta W, and the energy release rate G. And again, for symmetric cracks, we note that the two addends entering the expression of G correspond to the mode 1 and mode 2 contributions. It can be demonstrated that for asymmetric cracks, the standard VCCT may yield physically inconsistent negative values for G1 and G2. To overcome this drawback, a revised physically consistent formulation of the VCCT has been developed. A new decomposition of the crack tip force is obtained by considering energetically orthogonal force components. Figure A on the left-hand side of the slide show the forces corresponding to mode 2. When we calculate the mode 2 contributions, we apply only a force in the x direction, and we impose that the relative displacement in the x direction is completely closed, while the relative displacement in the z direction may be further opened or partly closed. On the right-hand side of the slide, in figure B, we see the second step, which corresponds to mode 1. And in this case, we apply the forces in the z direction and the remainder of the forces in the x direction. And the work calculated during this second step corresponds to the mode 1 contribution to the energy release rate. The expressions for the forces corresponding to mode 2 and mode 1 are given in the slide, and the details can be found in the cited papers. Anyway, the modal contributions to the energy release rate can be calculated based on the expressions below, and it may be noted that contrary to the standard VCCT, with these revised formulations, G1 and G2 turn out to be positive definite quantities. The coefficients Cxx, Czz, etc., entering the expressions for G1 and G2 are flexibility coefficients. These can be calculated based on the finite element mesh with the extended crack by applying unit forces at the crack tip nodes in the x and z direction. And the flexibility coefficients simply correspond to the relative displacements in the x and z direction. Once we have computed the flexibility coefficients, we can calculate the relative displacements at the crack tip produced by any assigned crack tip force, thanks to linearity. It may be useful to introduce vector notation, so the force components Fx and Fz are collected into vector F both face, and in the same way the crack tip relative displacement components delta Ux and delta Uz are collected into vector delta U. The crack tip flexibility coefficients can be collected into a symmetric and positive definite matrix C, and we can write the relationship between the relative displacement delta U and the force F in matrix form. We can also consider the inverse relationship, which gives the force F as a function of the relative displacements delta U, where K is the crack tip stiffness matrix, which is again symmetric and positive definite, and it is the inverse of the flexibility matrix F. The conical section associated with the matrix F turns out to be an ellipse gamma, which has been called the ellipse of crack deflexibility. This ellipse is useful to visualize the relationship of the crack tip force F and the corresponding relative displacement delta U. It works as follows. Consider the direction of the force F passing through the center of the ellipse. The direction of F intersects the ellipse in a point. At this point, take the outer normal to the ellipse, and this will be the direction of the relative displacement delta U. It is easy to determine the directions x over bar and z over bar, which respectively correspond to relative displacement delta U parallel to the x-axis and to the z-axis. This means that when the crack tip force F has the direction of the x over bar axis, the relative displacement will have only an x component. It will have no component in the z direction, and conversely, when the crack tip force F has the direction of the z over bar axis, the relative displacement delta U will be parallel to z, which means that no component in the x direction will be present. So the x over bar axis corresponds to crack tip forces F, which give rise to a null relative displacement in the z direction, which means that there is a contact between the cracked faces. All F vectors having the tip in the half plane below the x over bar axis correspond to a negative delta uz, which means that the elastic solution predicts interpenetration of the crack faces, the yellow area in the figure. On the other hand, if we consider forces F having the tip lying on the half plane below the horizontal x-axis, which is the red area, these correspond to compression at the crack tip. To make a long story short, the expressions given in previous papers for G1 and G2 strictly hold only in the white area above the x and x bar axis. When we are in the red, in the orange, and in the yellow regions, G1 and G2 have to be computed, accounting for the interpenetration of the crack tip faces, and suitable constraints have to be introduced to prevent this physically unacceptable interpenetration. What may happen is shown in these pictures. Figure A shows the initial crack. Figure B shows the extended crack. It may happen that the crack tip C splits into 2 points, C minus and C plus, and the relative displacement in the Z direction between these 2 points, delta UZ, is negative. So to prevent this, we may introduce a suitable contact pressure force P at the crack tip node, and the closure of the crack has to be considered starting from this new configuration. Figure D shows the forces that have to be applied to close the crack, and the corresponding work can be related to the energy release rate and to its mode 1 and 2 contributions. Details of the calculations will be given in the full conference paper. Here I just summarize the results. 4 cases have to be considered in the computation of G1 and G2. Case 1 is when both the crack tip force F and the relative displacement delta U in the Z direction are positive or null, which means that we have an open crack, and this corresponds to the white region in the ellipse plane that we saw before. G1 and G2 have the expressions given in the slide, which are the same as those given in my previous papers. Case 2 is when the crack tip force Fz is still positive, but the relative displacement delta Uz is negative. In this case, the elastic solution predicts interpenetration, which has to be prevented. And G1 and G2 can be calculated based on the expressions given here. In general, again, we are in 1-2 mixed mode fracture conditions. Moving on to case number 3, this is when both Fz and delta Uz are negative. We have both compression at the crack tip and interpenetration of the crack faces. In this case, fracture mode is a pure mode 2, so G1 will be equal to 0, and G2 can be calculated based on the expression given here. And lastly, case 4 is when the crack tip normal force Fz is negative, but the relative displacement delta Uz is positive. In this case, we have compression at the crack tip. Again, we are in pure mode 2 conditions. G1 is equal to 0, but G2 has a different expression as given here in this slide. The 4 cases, 1, 2, 3, and 4, correspond to the white, yellow, orange, and red regions in the ellipse plane. To conclude, we have recalled how the standard VCCT may yield physically unacceptable, inconsistent negative values for G1 and G2, and a revised physically consistent VCCT has been proposed in previous papers, where the crack tip nodal force was decomposed into energetically orthogonal components. However, such a revised formulation does not take into account the shortcomings from possible interpenetration of the crack faces, which may be predicted by the linearly elastic solution. In the present work, we have introduced suitable contact constraints to prevent this possible interpenetration of crack faces and deduced analytical expressions for G1 and G2 to cover all the possible cases. Numerical examples will be presented in the full conference paper, and future work will be necessary to extend further this formulation to introduce also the effects of friction between the crack faces. Thank you very much for your attention.